Hello everyone, my name is Andi Zaky Ashari, and now I will giving some brief explanation about the edge that I've made. This is the LSTM architecture used for predicting the regression for Apple company, especially for their stock prices. Firstly, I have created 6 different architecture, including one for baseline, and the other 5 is the modified model involving the hyperparameters tuning to achieve the optimal results. As usual, when we are working for the data, first I load the dataset, and now we are moving to the first step, which is the data understanding. And the first thing I do here is transform the date into datetime type and then grouping the data by year. This is to visualize the closing price annually for Apple company. As we can see here from the plot, the Apple went public from 1980 with the ticker name of AAPL, which is Apple. And then, however, the value of Apple remained relatively flat until around 2007 when Apple launched its first generation of iPhone. As we can see here from the plot, the Apple company went public since as we can see here from the plot, the Apple company as we can see here from the plot, the Apple company went public since 1980 with the ticker name of AAPL, which is Apple. And however, the value of Apple remains relatively flat until 2007 when Apple launched its first generation of iPhone. And since then, the market value of Apple has skyrocketing until now. And then we are still in the data understanding section where I will print the data information, the head of data, and then the descriptive statistic for Apple dataset. Where we can see the data information for Apple dataset. There are 8 columns, including 1 variable for date time, 5 for float or decimal, and 2 for integer value. This dataset has no missing value. And now we are heading to the head data, where we can see the first 5 lines of the dataset. And now we are going to see the head data for Apple dataset, where we can see the first 5 lines of the dataset, which is including the date, open, high, low, close, adjustment, close, and volume year columns. And now for descriptive statistic for Apple company. And now for descriptive statistic for Apple dataset, we can see here the descriptive statistic of Apple dataset. As we can see here, we can see the mean for closed dataset is around 32.69 USD and the standard deviation of approximately 58.47. And then since this dataset spans from 1980 to 2020, making it valuable for analyzing a long-term trends and the pattern in Apple stock performance. And next we move into the data pre-processing and splitting. This section, and now we are moving to the data pre-processing and the splitting data. This section involves the selecting variable. This section, and now we are moving to pre-processing and splitting data. This section involves selecting the relative variable, and now we are moving to the pre-processing and splitting data. This section involves for selecting relevant variable, namely date and close, and then I also sort the date from past to present, and then set the dataset as index since we are working with time series results. We can see here the date already as an index, and our data frame only consists a date and the close value for Apple stocks. And furthermore, I normalize the close data, and furthermore, I normalize the close variable using min-max color, and furthermore, I normalize the close variable in the dataset using min-max color, and afterwards, I define the window size of 5 and the horizon of 1. Window size is input and the horizon is the out. And then after this section is completed, now I proceed to split the dataset into 80% of training, 10% of validation sets, and 10% for test set. And now moving on to the modeling section, which is the first architecture is baseline architecture. The first architecture, which is the baseline architecture, consists of a single LSTM layer with 50 units, and then the activation using value. And then now we are moving on to the modeling section, which is for the first baseline And now we are moving on to the first modeling section, which is creating the baseline architecture. This baseline architecture consists of a single LSTM layer with 50 units and the activation function using rally and the input shape of the window size, and following with a dance with a single out. And this model compiled with Adam optimizer and the mean square root or MSE loss function. And then this data is trained with the training data with 50 epoch and 32 of batch size. From the first epoch to epoch 50, you can see here that the validation row is relatively very small because this performance is quite good. And then once the model is trained, you can apply it to the test set to predict the data. And I also transform the predicted data to predicted data to the actual data, and then I also transform the predicted data to the whole scale. And as the result, you can see here, that the RMSE or root mean square error. And as we can see here, the result for baseline model performance, you can see that this baseline model show promising performance in predicted stock prices. The RMSE value of 5.02. The RMSE value, as we can see here, that the result of this baseline model is showing that this model shows promising performance in predicting stock prices, with the RMSE value of 5.03 indicates a relatively low average prediction error. The MAE of 3.45 is suggests that on average this model's prediction divided by a small margin of actual value. And then the MAPE of 1.89, this indicates a relatively low average percentage of error. And then additionally, the R square or R2 scores is 0.99 or 99%. This indicates that this model explains a significant portion for the variance in the data. However, let's try to modify the architecture to get some better value. For the first modified architecture, this model involves using two LSTM layers, where the first LSTM layer is 128 units using the patient value, and then the return sequence is true to maintain the sequence of the out. And then the second LSTM layer consists of 64 units and the same activation is relevant. And then the first dance layer consists with 32 units and value activation, with following with the last dance layer using a single output unit. This model compiled using Adam and the loss with mean square. And then the model is trained with 50 epoch and 32 path size. We headed to the result of this first performance. Once this model is trained, you can see here that the result of the first modified model is, and then as we can see the result of modified model performance. Based on this result, there is a slightly increase in evaluation matrix compared to the baseline model. This model has RMSE of 5.42, indicating a slightly higher average predicting error compared to the baseline. And then the MAE value of 4.32 suggests a higher average deviation from the actual value. And then the MAPE value of 2.6, this indicates a slightly higher average percentage error. And then the R2 score of 98% shows that this modified model explains a slightly lower portion of the data variance compared to the baseline. Overall, these modified architectures still demonstrate a good performance, but it falls slightly behind the base model. Let's try again to create the second modified model, which is the modified architecture 2. Since our last modified has a slightly lower value than the baseline, now I'm trying to use the grid search function to search the best hyperparameter that I could get. This grid search CV is a powerful method from scikit-learn library that allows us to systematically search for the best combination of hyperparameter for our modified model. First, I define the function to creating the Keras model to create the object of Keras regression to plot the modified model. And then I set the hyperparameter where the grid search CV will search the best combination from these two variables, units and optimizer. And then after we are using the parameter grid to search the best combination of hyperparameter, we get the result of the best hyperparameter is using optimizer Adam and units of 128. And now we implement the best hyperparameters to our training data with 100 epoch and 32 batch size. And now we can see here that the result of modified model 2 performance turns out this performance is as not good as the baseline model, as the first modified model. So now I'm going to tune the hyperparameter manually to get the best result. Moving on to the modified architecture 4, I'm still using two layers of LSTM. The first layer of LSTM consisting 254 units and using activation function value, and then the return sequence is true, and the second LSTM layer is 128, and then the first dense layers is 64 units, and following with the last dense layer consists of a single. This model compiled with the same optimizer, which is Adam, and loss function is MSE. And now I decrease the epoch size to 50 epoch and the batch size to 32. After the data is being trained, we can see the result of this performance for model 4. The result is slightly better than our previous baseline model, and the previous modified model. You can see here that the grid search CV is not really giving any impact to our model performance. Manual tuning can give me some better performance. But let's try to tune the hyperparameter again to get some better performance that I could get. Now moving on to the fifth modified infrastructure. In here, same as the model 4, I will increase the number for all layers, and for the first LSTM layers using 512 units and still using activation value and return sequence is true. The second LSTM layers using 256 units, and the first dense layer using 128 units, followed by the last dense layer consists of a single out. All models I use in my code using DAM optimizer and loss function of MSE. In this model 5, I increased the epoch size to 100 and the batch size is 64. As we can see here, that the performance result of modified model 5, we can see that the model 5 has a slightly below the model 4. The model 4 demonstrates a better performance compared to this model because the model 4 achieved a impressively lower LMC, a lower MAE, and a slightly higher MAPE, and a higher R2 score. And in contrast, model 5 exhibits a slightly higher RMSE of 0.01 and a lower MAE of 0.01 and a lower MAPE of 1.68% and a slightly lower R2 score of 0.9912. And considering this, I will proceed to create a new model, which is model 5, to further improve improvement for predictive performance. And now we are headed to the last modified architecture, which is the model 6. Same as the previous model, I only increase the unit value for all layers and also increase the epoch and the batch size. The reason why I increase the unit value, epoch, and batch size is to increase the model's capacity to capture more complex pattern and potentially improve its ability to increase the relationship in data, allows the model to continue learning and refining its weights over the extended period, And also it can help the model to converge to a better solution to its performance. And also a larger batch size can result in more stable gradient update and potentially leading to a faster convergence and a better generalization. For the first LSTM layer, I use the number of units, and for the first LSTM layer, I use 1024 units. This is quite high. And for the first LSTM layer, I use 124 units, which is quite large. And the activation function remains the same for all models, and the return sequence is also true. And the second LSTM layer consists of 512 units. The first dense layer consists of 256 units, and the last dense layer with a single output unit with the same model optimizer of Adam and the loss function of MSE. This model is trained with epoch of 200 epoch, and the batch size is 128. And headed to the performance result for our model 6, we can see that the model 6 has the lowest RMSE value and the MAE value, this implying a better accuracy to predict the stock prices. The MAP value, the MAPE value suggests that the average percentage, the difference between the predicted and actual value is around 1.34%, which is relatively very low. And additionally, the R2 score or R square is 99.29% of or 99.3% indicate that this model explains the variance in the target variable, signifying a strong fit. And now we can see that this model 6 is the best model on the performance for predicting the stock prices of Apple company with a large number of units. We can see that the large number of units can giving us the best result. Thank you.